Now that we know our data pairs have a strong positive correlation, we can find what's called a least squares regression line, or a best fit regression line. The goal here is to find a linear equation that best fits our data. Since the data is not perfectly correlated, the data points are not in a perfect straight line. But we can try to draw a line that misses the data points by the least amount. You can see here on our graph we have this least squares line already drawn. The idea here is to make a line that minimizes what's called the residuals. The residuals are the distance from the data points to the best fit line that's drawn. The residuals are the red line distances shown on the graph. And the best fit line is a line that minimizes the sum of all these residuals. We don't have to worry about actually calculating these residuals. Instead, the equations we use to find the best fit line will do the work of minimizing those distances for us. The line that we have drawn is a straight line, and the equation for that line can be given in slope-intercept format. We should be familiar with that format. It is y equals mx plus b, where the m value represents the slope of the line, and the b value represents the y-intercept. When we want to find an equation of a line, we need to solve for the slope and the y-intercept. For a regression line, the formulas that are used to find those values can be seen on the screen here on the left. The slope calculation uses some of the same summations as our correlation coefficient calculation did. And the formula for the y-intercept uses the value we will calculate for the slope, along with x bar and y bar, which represent the means of the x and y data values respectively. We should first calculate the slope of our best fit regression line. Just like before, I would break the calculation into 4 parts. The first part would be n times the sum of x, y, which would be 5 times 4,280. The second part would be the sum of x times the sum of y, 35 times 550. The third part would be n times the sum of x squareds, which would be 5 times 343. And the fourth part would be the sum of x's squared, which would be 35 squared. Following order of operations, I should do all 4 of those multiplications first, yielding me the 4 values seen here. When I do those subtractions and divide, I would end up with a slope value of 4.388. After I calculate the slope, I would then want to calculate the y-intercept. That can be done by taking the mean of the y values and subtracting the slope times the mean of the x values. So I have to calculate the mean of the y values, the mean being the sum of y, 550, divided by n, which is 5, giving us 110. And for the x values, the sum of the x values is 35, divided by n would give us 7. I can now use those values of 110 and 7 for y bar and x bar, plug them into the slope formula, and I would get a y-intercept of 79.284. At the conclusion of these calculations, we should have an equation that could estimate a value for y, which would be annual sales, based on a value of x, which would be the years of experience. Our final equation is y equals 4.388x plus 79.284. And we can plug in any value for x we would like to estimate a value for y. The example on the screen shows us that if we want to estimate the annual sales of an employee with 15 years of experience, we would plug in 15 for x and get a value of y that is about 145,000. The last topic to discuss is something called the coefficient of determination. This is different than the coefficient of correlation. The coefficient of determination is the value r squared. To get that value, you would simply need to square the r value we calculated previously, which was 0.971. The coefficient of determination is a tricky topic to understand. Officially, it is the ratio of the explained variation of our data compared to the total variation of our data. In simpler terms, it is a measure of how much of the change in y is explained by the change in x. Since we now have a regression line, we have an estimate of what we think y should be based on a specific value for x. But we are assuming that the change in y, annual sales, is solely dependent on the change in x, which is employees' experience. In reality, that is probably not the case. Based on our data, we know there is a strong correlation between those two variables. But there will always be some other unexplained factor that affects y other than the variation of x. The r squared value gives us the percentage of variation that is explained by our new regression line, while the remainder of that percentage we would say is unexplained.